All right, so I mentioned we're talking about single phase power. This is what single phase power really typically looks like in your house, right? You get two voltages that are effectively 180 degrees out of phase with each other. So if they're 180 degrees out of phase with each other, that means when one of them, this is what the infinity here, one of them's going peaking, the other one is troughing, right? Negatively peaking. So that means if I subtract the two of them, what would I get? I get 240 volts with an angle of 0 degrees. All right, that's what I would end up with. All right, so we said there's, in your house, you really kind of have two phases. We don't call it two phase. All right, it's single phase, right? So in this case, what I'm trying to show is some of the loads would be, these are 120 loads here, like what I'm trying to show with these two, but they have two different voltage sources that are provided. And then I got loads like my air conditioner or my oven, whatever, that will be 240. Okay, it doesn't, the same rules apply if I'm looking at them. All right, so we went through last time and I just kind of talked through the basic ideas of single phase power, right? And so single phase power basically comes from the fact that what I do in reality, what you learned in network one, all the way back there was that power is V times I. In AC context, that means I take a V of t times an I of t. So my V of t would look like what I have here, right? Some peak value, some time domain waveform, some time domain waveform for the current, multiply those together and I get that wacky looking thing right there. And what we talk about is the values that I have in those blue boxes. The first blue box is really important. We call that P, capital P. What's capital P? Real power or average power, right? What is it physically? What the heck does it mean? It's the average power. So on average, it's basically the rate at which energy, electrical energy, is being converted to some other form. And that's what this class is going to be about. Okay, this will be the rate at which I'm converting electrical energy into light and heat in a light bulb, or into mechanical work if it's a motor, right? And then Q, what is this Q? Reactive power. What the heck's reactive power? Yeah, it relates to what's going on with the storage in the system. If Q is 0, there's no storage, right? It's only doing energy conversion. All right. If Q, what do I need to have Q? What does my load need to have for there to be Q? It has to have an inductor or capacitor. There needs to be something with storage. Okay. So, I went through you can look at these examples again to talk about that. But the important thing really is I narrow it down to a couple of important quantities. And so what we talked about is if I think about the voltage being, so as a phasor, right? Again, I'm using an RMS all the time in all my phasors here. So I have VRMS, IRMS, right? And so if I take the voltage and current that are applied to a load, like what I have right here, if I looked at P and I looked at Q, right? If I look at the formulas that we got from just doing V of t times I of t, I got this for P and I got this for Q. All right. Now, what have I written here? I've said that it's phi v minus phi I as the angle in there for that cosine, right? What is phi v minus phi I? What does that relate to?
Is that fine? Or are they not Z?
Well, it relates to the impedance, right? Which could be inductive, it could be capacitive, right? So that came from Ohm's law, right? I have V equals I times Z, right? Remember, that's two equations right there, right? There's one for the angle, there's one for the voltage, right? What's the one for the angle? Well, it's the angle of the voltage equals what? If I turn this into an angle equation. Yep, 5I plus 5Z. So what I see when I do this here is this thing, this P and Q, they form the components, the real and imaginary components of a vector. There's no such thing as imaginary power. It's just somebody noticed that, well, I defined this thing Q and I defined this thing P, that I can turn those into a vector, right? And what I see from that, because of the way these guys are set up, if I look and I have V and I defined like they are as these phasors, then what I find is that I get complex power, right? I get this thing S, all right? which is equal to P plus JQ, it is also equal to V times, not V times I, but what? I conjugate. Which is to say that if I think about what it is, when I multiply those two vectors, it's the magnitude, the two magnitudes multiplied, and then it's a vector that has an angle of whatever the angle of V is minus whatever the angle of I is, or whatever the angle of Z is, all right? Now, the other term that we define is what we call the apparent power, which is the magnitude of that vector. All right, apparent power is not a vector, it's the magnitude of the vector. All right, so in my table here, I've got a summary of all this stuff, a whole bunch of different things that are there. All right, and so you'll find that useful probably as you're going through and doing problems, which is what we're going to do now. Okay. All right, now this is a pretty classic sort of problem. And to be clear, I'm saying a load is 10 kVA and all this sort of different stuff. When I deal with loads in general, this is, if you go to the utility or whatever, this would be what they would make the assumption of for a bank of houses. So if I had like 5 houses connected to a transformer, and we'll talk about transformers later, right? If I had 5 houses connected to a transformer, I'll say that they have a certain amount of kW at a certain power factor, right? That's the peak condition, right? Utility is most concerned with the peak condition. What's the highest power you're ever going to draw? Okay. And most likely the highest power that they're going to draw was this morning, right? The highest peak in the system is probably on the coldest day of the year, all right, at 6 or 7 a.m., somewhere around there. So today was probably the peak day, all right, because it was so cold outside. All right, so that's where you use this stuff, is you talk about what's the peak condition, you make sure you want to see how the system's going to operate in those conditions. So here's what I've got. I got 2 loads in parallel. All right, could be 2 houses connected into the grid. They're rated apparently for these two values. Load 1, it says 10 kVA with a power factor of 0.9 lagging. And then the other one's 12 kW with a power factor of 0.85 lagging. So we got some words to unpack there, right? And then I got all this other stuff. Frequency is 60 hertz. I know that the voltage across these 2 loads is 208 angle 30 degrees. All right. And I'm told that this thing's connected to a voltage source through some LR series circuit. All right. And I got a series of questions. So I wrote here basically what's the power triangle for load 1 and load 2, the phasor diagram for load 1 and load 2, the current phasor IS. So what's that? Current phasor IS is basically what's the total current going into the combination of the loads. And then I'm trying to figure out what is the voltage source V sub S. Okay. Now, the last thing I say here is I want to add a capacitor in parallel to the loads to make the power factor unity. Now, that's something that you may or may not have covered in 2112, but we're going to talk about that. All right? These problems are pretty straightforward, but we got to unpack here a little bit of what information did I give you here for load 1. And first of all, I said this thing about the power triangle for load 1. What I'm talking about is there's the complex power vector S1. Right? S1 is equal to P1 plus JQ1. Right? When I'm talking about the power triangle, I'm talking about trying to figure out what's P, what's Q, and what's the magnitude of S, trying to draw that whole thing out. All right? Same thing for load 2. All right, so what do I know for load 1? What have you been given?
You know, the
For load 1, okay, I'm glad I asked, right?
you see the Q, because it's VA.
I know the S.
That's
Yeah, right. So when I have kVA, so if I don't remember, I can go back to this table here. So I give you the units. Apparent power, and it's not this way in the notes that I posted. The parent power is the magnitude of S. All right, I know I fixed that in the notes that I posted. The magnitude of S, which is VRMS times IRMS, is in units of volt amps. Real or active power or average power has units of watts. Reactive power has units of VARs or volts amps reactive. All of them are volts times amps. We just differentiate them differently. All right. So if I see VA, I've given you the magnitude of that thing. So I've also told you the power factor is 0.9 lagging. What have I told you by telling you that the power factor is 0.9 lagging? What is the power factor?
It's cosine. That-
Cosine of the angle. So if S, so as I've defined here, right? S is the vector. So I'm doing the power triangle. I'm saying I want to get what's this side, and that side. So what have I given you? I've given you this side, right? I gave you the hypotenuse of it. And by giving you the power factor, I gave you this angle. There's the trick. Cosine, for all of these loads that I'm talking about, for real loads, inductive or capacitive loads, they are only going to be in quadrant 1 or quadrant 4. So in other words, only here, this is 1, this is 4. I'm only going to have stuff in those two angles or in those two quadrants. What's true about cosine in both of those quadrants?
Angle of the cosine of the positive and negative angle
Is the same, right? So if I give you a power factor of 0.9, you don't know whether that is the positive angle or the complementary negative angle, right? So I need to give you more information to be able to figure out which one it is. Okay. Do you have a question there?
I was gonna say that since we did for CF value itself, is that just P divided by S? I'm not saying.
It is. So it is P. So because of the way this guy is set up, yeah, the power factor is always P divided by S, but I can't tell whether this angle here is negative or positive. Because if let's say this angle was 30 degrees. Cosine of 30 and cosine of negative 30 is the same.
But wouldn't you figure that out from doing,
From the information I gave you, you wouldn't have enough unless I tell you this piece,
right?
that it's lagging, right? So when I told you that it's lagging, what does that mean?
Positive.
Tells you it's positive. So lagging basically means that the load that I have, this load 1, is an inductive type of load. In other words, the load that's included, what's that?
Why do we consider positive?
Well, so it's when I say it's lagging, what I'm saying is the load has a lagging power factor, which means that the load needs to be inductive. Somehow it has an inductive impedance, because what's true about an inductive impedance, an inductive load always has its angle in the first quadrant between 0 and 90 degrees. So we went through, why that happens last week. You can go back and review that. But basically, for an inductive type of load, it's going to be a positive angle. Sometimes I like to use the word power factor 0.9 inductive. It's more common to call it a lagging power factor or a leading power factor, right? Both of these are lagging. That's more normal. You don't come across a lot of capacitive loads. You come across more loads that are inductive, all right? And why would that be? Any idea? Why do I have more? I can make up a problem that has whatever, right? But in the real world, why is there more lagging load than leading load? Why more inductive load than capacitive? Any ideas? Well, so yeah, so there's transformers in the system for sure. But if I look at these loads, like your house doesn't have any transformers, probably.
Does it help like increase the amount of time because the larger the distance?
Well, you're starting to think about the transformer stuff, which we'll talk about later. But if I think about what's inside, what's in your house? What's the stuff you're plugging in?
Right. Bunch of resistors.
There's mostly resistive type of stuff or motors. And what's a motor? A motor is iron and wire, which is an inductor. Okay, so we're gonna talk more about motors later, but that's basically the majority of the loads out there in the world are computers, light bulbs, and motors, right? So they're fairly straightforward devices. And they tend to be inductive, if anything. Okay. Computers, that kind of stuff, I gotta be careful. They're actually more complicated. All right, but because they're electronic. We'll talk about some of that later, but for the most part, they're just a P. All right, they're resistive like. All right, so let's deal with load number 1 then. So for load number 1, what did I say? We said that what I gave you is the magnitude of S. All right, so I said the magnitude of S is, what did I say? I keep going back. What is it, 12 kVA? 10 kVA, thank you. The other one's 12 kilowatts. This is 10 kVA. And I said that the power factor is 0.9. It's not the sine, it's the cosine. Cosine of phi z is 0.9. So before I get too far down the road, all right, what I know is this guy's going to be like this. So this is Q. We know it's in the first quadrant, yeah. So I know that here's phi z1, right? And I know which one of the sides do I know here?
The hypothesis.
Yeah, I know the hypotenuse, yep. That's okay. So if I want to figure out P and Q, how do I do it?
Find that first.
You can find the angle first to find either P or Q. Now, somebody had actually said already too that, you know, one thing I can do, because P is equal to the magnitude of S times the cosine of phi z. Right, so I have that. Q is equal to, right? So I can look at this, you know, I don't need to think about those formulas. I can think of this thing just as a triangle and use my trigonometry, right? So I got lots of different ways that I could solve this thing. I think I could figure it out without even, if I wanted to, I wouldn't even need to solve for phi, for what the angle is, right? I could say, if I know S and I know cosine, I could say 10 kVA times 0.9 is equal to 9, what units? So 10 kVA times 0.9. Yeah, this would be 9 kW. All right, 9 kilowatts. Now, what about for Q? I could solve for the angle and use this. What other thing could I do to solve for Q? Yeah, I guess so. I want to use something else.
Oh,
Yeah, I could say that with this triangle, I have S1 squared has to be equal to what? Yeah, square root of P, well, S1 like that is P1 squared plus Q1 squared, like that. So I could solve it that way too, right? Because I know now what S is and I know what P is. So I got a couple of different ways to do it. I could figure out phi z, which I'm going to need anyway, so let's just do it. Phi z comes from P1. Now, what is it? What is it? Yeah, it would be the inverse cosine of 0.9. Yes. Well, so yeah. So it would be, I was looking for the answer. Inverse cosine of 0.9. Now, this is the thing where if I had told you it was a leading power factor, I would have said inverse cosine of 0.9. I would have had to say, put a minus sign in front of it. All right. Arbitrarily because it was leading. All right. So this works out to, if I do the math, 25.8419 degrees. Now, if I were in MATLAB, what would I do? If I did in MATLAB, it would be ACOS, right? If I did ACOS, it would give me an angle in radians because it's a trig function. MATLAB assumes everything's in radians, right? Now, if I got that, what I probably would do is I would multiply by 180 over pi, which is just a unit conversion. You can also do degree deg to rad. You could also do A cos D if you wanted to, right? There's a couple of ways to do it. All right, now, yeah, which is there's a set of functions in MATLAB. If there's a trig functions with a D after them, assume a degree input. All right, so there's a set of those. I think I put on the Canvas page the other day sort of a listing of some of those functions.
Can you go back to slide one?
Sure. All right, so, and I guess what I didn't write here too is I want to compute what the Q is, right? So if I compute the Q, what will that be? Q will end up being, if I run those numbers, I'll end up with 4.3589. And what units do I use? K bar. right? How many kVARs? So, all right, then we have, and again, that's Q1, I guess specifically, because I'm talking about that load. Now, how did I, so this is how I set up my MATLAB code to do the calculation. So I set up a bunch of stuff here that I'm going to need later. All right. So we'll get to that in a little bit. S1 mag and PF1. So I basically said the magnitude was 10 times 10 to the third. So 10e to the third is MATLAB's way of including exponential notation. And I said the power factor is 0.9. So what I did to get the angle here was I said A cos power factor 1 times 180 over pi. A couple of ways we talked about you could do that. And then I did my P1 and my Q1 like I wrote there. All right. Now notice here, you got to be careful. The thing's going to annoy you is if you computed ang1 here, like I did, this is now in degrees. When I go to sine, sine's going to expect an input in radians. So I just, instead of putting in the variable, I did A cos power factor 1. All right. One of the things you should get comfortable with MATLAB, which you guys don't do, I see you guys do this all the time. You'll solve and get the answer to one part, and then you'll handwrite it into the next part. When I say handwrite it, meaning you'll hard code it in. I would recommend that you get comfortable with variabilizing, scripting everything. So that way, if you make a mistake in one spot at the very beginning, it fixes everything, right? Rather than trying to carry it through. Especially if you're more of a computer engineer, you want to get comfortable with that kind of thing, right? Scripting it is helpful.
You're saying to actually like run the code like you have there,
Right. You can do it however you want, right? Whatever you're comfortable with. But if the tool is designed to operate that way, you might as well use it that way. Yeah, that's a good way to work, right? So then you want to get comfortable doing it that way is my suggestion. Because anytime you're hard coding stuff, if you make a change, you're going to forget to go back and change it somewhere else, and then you're going to be scratching your head. Yeah, that's right. It makes it a lot easier to debug what you're doing. Yeah. Okay. All right. So now let's do the triangle for load 2. All right. Load 2. So what was load 2? Load 2 was 12 kilowatts with a power factor of 0.85. All right. What's that? What have I been given? Given the power. I've given P and the power factor. Now maybe I should have chosen leading, but I chose lagging. So lagging means that it's an inductive load. So what quadrant is this? First quadrant. Yeah, first quadrant. So, all right, let's do our calculations here. So I was given that P2 is 12 kW. All right. They're talking like household type of loads, right? That's where these numbers are coming from. And I'm told the power factor was 0.85, which for a house would be a really bad power factor.
Bigger the power factor for house.
It's a good question. It should be above 0.9. I think in Duke's standard calculations, I think what I've seen, they assume about 0.93 for a house. Usually they don't know exactly what it is, but it's usually over 0.9. I'll give you an example. We'll talk about this later, but usually for an industrial customer, it's usually above 0.8. Industrial customers are the ones that have low power factors. They got big motors doing stuff like chopping wood or various grinding things, pumps, all sorts of stuff. All right, we'll talk about a lot of that sort of stuff later. All right. In fact, maybe on Friday, what I'll do is I'll show you what a commercial bill looks like where you actually get a power factor charge. All right, because that does happen. Let me not get too far away from what is important. So we want to figure out, first of all, just how to draw the power factor, the power triangle here. So, all right, which sides, if I draw the triangle, I'm in the first quadrant. What do I know? I know the real part, right? So I know this guy. This is P2 here. And I don't know, because it's 0.85, I know that it has to be a bigger angle than it was before, right? Just because I know enough about cosine. So I don't know Q, and I don't know the magnitude of S. All right. So this would be phi Z2. So where do I start? So first thing I'm gonna have to do here is probably, I could figure out S, the magnitude of S, right? How could I figure that out? given those two things, how can I figure out the magnitude of S? What's P equal to? And if you could use, let's use SOHCAHTOA. Let's not even think through, let's just imagine, I got a triangle here, right? So how, knowing P and knowing this, the cosine of this angle, what's the cosine of an angle or a triangle here? Yeah, adjacent over hypotenuse, right? So if I have, so, right, the magnitude of S2, that's the hypotenuse. Right? No. The adjacent is P2 over the hypotenuse is equal to cosine phi Z2. But I don't have cosine of phi Z2. Or do I?
Yeah.
I do. I get the power factor, right? Power factor is 0.85. Right? And so that, if I go through the math on that, yeah, 31, exactly. I get that the angle here, phi Z2, works out to be 31.7883 degrees. And I get that the magnitude of S from this whole thing, right? The magnitude of S works out to be 14.118, what units? kVA. Okay. And then Q, how would I get the Q in this case? Knowing what I know, how would I get the Q? Yeah, so I could, there's a lot of ways to do this, right? I could say that sine is related to opposite over hypotenuse, right? So Q over magnitude of S is the sine of that angle. Or what he just suggested, I could use tangent, right? But tangent is opposite over adjacent, right? Is equal to the tangent of the angle, right? If I go through either of those, I get that the Q is 7.4369 kbar. All right.
Do you always recommend rounding for 4 decimals?
Not necessarily. Yeah, that's a really good question. You'll see I'm always going to use 4 decimals because that's what MATLAB outputs by default. In reality, I mean, it would be really, really weird for somebody to say the angle is 31.7883 degrees. No one knows an angle of that precision. At best, you'd say 31, probably say 30, to be honest. So normally, in fact, with something like this, I would probably say 14 kVA and maybe 7.4 kvar, right? If I was talking in reality. Now, I just take the number when I do these and I just take them out of MATLAB. But I would, in practice, it's probably more like 1 digit after the decimal. That's a good question. Especially with an angle. You would never do an angle with that level of precision. You guys have seen protractors back in the day at some point, right? You can't get an angle to that kind of precision. And it doesn't matter that much. If I took the sine of 31 degrees versus the sine of 31.7, you wouldn't notice the difference. All right, and then here's how I did the calculation for that. So you guys, when I post these, you guys can look at my calculations to see how I did it here. All right, now what I want to do is I want to figure out the phasor diagram for the loads. Okay. So to figure out the phasor diagram for the loads, I got to go back and look here. All right, so sketch the phasor. What the heck do I mean by the phasor diagram for load 1? When I say that, what do I mean? Big words. Phasor diagram. It's just, yeah, yeah. Is it great? Yeah, basically it's the voltage and current. Yeah, basically there's going to be 2 vectors as he made the hand motion. Yeah, it's going to be 2 vectors, right? So it's basically the vector for V and I. So what vector am I talking about? What vectors here? So the voltage vector and the current vector. So the voltage vector, I gave you the voltage across the load, which apparently here is 208 angle 30 degrees. All right. So 208 volts with an angle of 30. That's an RMS value. That's a pretty standard RMS value, 208. All right. So, if I draw my phasor diagram, My voltage is somewhere over here. VL is over there. And I got to figure out where IL is. How do I figure that out?
By using
By using S. Yeah. So what do I know with S? S is V I conjugate. Yeah. And if I'm doing load one, I call that I1. Right?
V_2.
Well, so I called it VL. Technically the voltage, since they're in parallel, the voltage is the same. Right? The currents are different, but the voltage across them is the same. I just called it V line. That's what L usually means, is line in this case. All right, so S1 is that. Now, what do we already know? We already know what the magnitude of S1 is. All right, we were told that. So the magnitude of S1 was 10 kVA. What's that equal to? Based on this equation here, without going back, we can go back to the table. It's in the tables. I have many tables. But if I told you, based on that, if S is equal to V times I conjugate, and I know S, the magnitude is 10 kVA, what's true about just a vector relation? There's a lot of formulas with this stuff, but it's really not that hard, right? It's basically just a vector relationship. I have vector equals vector times vector. If I have vector equals vector times vector, how do I get the magnitudes there? How do I write the magnitudes? Well, yeah, so 10 kVA here has to be equal to the magnitude of VL times what? Magnitude of I1. Right? Technically, it's the magnitude of I1 conjugate, but what's true about I1 and I1 conjugate? What's true about their magnitudes? Same, right? So basically, I have that relationship here. I know what the magnitude of VL is. I said that was 208 volts, right? So this is equal to 208 with, and then I'd say it's multiplied by the magnitude of I1, whatever that may be, right? And then we solve for that just by algebra. And what do I get? I get that works out to be, in this case, 48.0769 amps. Okay. All right. Now, let's not get the full phasor diagram, right? What else do I have to do? Get the angle. Okay. How do I get the angle? Well, I can go back to Ohm's law, right? Or I know what's the angle of S here. So this is S1. What's the angle of that guy? Yeah, so I call it the angle of Z1, the angle of the impedance. That's also equal to the angle, as he said, of phi V minus phi I. Now, if I go back to what we said previously when we did the power triangle here, is I figured out that the angle of the impedance had to be 25.8419 degrees, right? So phi Z1 is 25.8419 degrees. And that's equal to phi V minus phi I. All right. Now, is that enough to, what do I know? And what am I solving for? I know phi V is 30 degrees, right? So then I figure out what phi I is. Phi I, and I guess specifically I want to call this phi I1, right? This is 30 degrees. So if I do the math, phi I1 is equal to 4.1581 degrees. And so that would put it somewhere over here, right? I1 would be over here. All right. What's that?
I was just saying, like.
Lagging, yes. So what, so how do I know that that's lagging? Why do I call that lagging? What denotes whether one's, when I look at two vectors, how do I denote whether one's leading and one's lagging? Well, which one peaks first? I'm looking at the time domain. If I'm looking at the phasor diagram, that's exactly how I would do it in the time domain. In the phasor domain like this, I'm looking for which vector is more positive. In other words, which one's more counterclockwise. So V is further along than I is. Right? Voltage leads the current. So when we use the term lagging, we're basically saying, okay, what's the current doing relative to the voltage? It's lagging the voltage. All right, that's the general terminology we use, was what's the current doing relative to the voltage? Is it lagging it or is it leading? If it was a capacitive load, I would see that the inductor, or sorry, I'd see that the current was more positive than the voltage. Okay. All right. For load number 2, I would do the same process. If you want to look at how I did this, right? So this is how I did it here, right? As I went along and I solved for all the different stuff. Now, one thing that you'll see, and I wanted to point this out because it gets to the question that was asked very beginning. For VL, I put VL in immediately as a vector, right? So VL was supposedly 208 angle 30 degrees. MATLAB has no way to deal with polar, but it can deal with the Euler identity stuff, right? The Euler form. So the complex exponential form. So what I did here was I wrote, instead of that, I wrote 208 e to the j 30 degrees, which MATLAB does not like the 30 degrees. Like I said earlier, exponential is a trig function, right? It's argument. So in MATLAB, exponential is exp. So what did I do here? I did e to the j 30. I wrote as exp j times 30 times pi over 180, which is converting that from degrees to radians. Again, a couple of ways to do that. You could have said that it was deg2 rad 30, right? That would have worked too, right? But there is no expd. There is no exponential degree. All right. So there's a couple of ways. What's that?
The degree.
You could, yeah, you could write that as basically exp j times like that, right? Or you could do it as a variable somewhere else, however you wanted to do it. Okay. All right, so that, so what I did here, if you notice, to get the phasor diagram, right? I created an S vector by saying S1 was P1 plus JQ1. And then what did I do to get the angle of I1? I took the angle of that voltage minus the angle of whatever that S1 vector was. And then I put that together into the I1 vector. All right, so you can tear that apart later. I'll put that in the notes that I post. Okay. All right. Load 2, what would I do? I'd do the same exact thing. All right, so I'm not going to go through that too carefully. All right, you can look at my code there. I'm going to end up with I2 equal to 67.8733 amps. In this case, with an angle of negative 1.7883 degrees. Does that one end up in the 4th quadrant? Which just means that with the voltage across it being, so the voltage is at 30 degrees. This guy's a little bit over here. He's less over here than I just drew him. But I'm just 1 degree is hard to show. He's lagging more, is what it means. And he should be lagging more because he has a lower power factor. If his power factor was 0, what would the angle between the voltage and the current be? Be a 90-degree shift between them. All right. Which would basically mean that the load was doing no real work. It was just basically your house is an inductor, right? Which would be useless. It would be a very dark house, right? It'd be very cold, but you'd be storing a lot of energy.
And when you said that the power factor was 0.85, it's not.
Yeah, that's pretty low for a house, 0.85. I mean, ideally, you'd want it to be 1. All right, I want to talk about that. So, my next question here was what? So we figured out, we did the first 4. I want to determine the current phasor I sub S. Okay, so here's the circuit. I sub S is the current going into, or basically coming out of the source there. How do I figure that out? Based on what I know here. I can add I1 plus I2, just a KCL, right? How would I figure out V sub S? I'd do a KVL around this guy, right? I'd say V sub S has to be equal to whatever the drop is across here, plus what V sub L is, right? So I would say that that's got to be V sub S would have to be equal to whatever I sub S is times, I called it R plus J omega L, right? Plus whatever that load voltage was, right? And you can look at my code for that here, right? So this is basically, I said VL plus I times R plus J omega L, right? I could do all the individual components. I could just let MATLAB do the work for me. All right. And I generally just tend to let it do the work for me.
But when you take the test, we're gonna have to. We can do a plug and chug in that.
You might.
You're saying some of our stuff would be on MATLAB code?
In other words, if I'm asking you to do your homework, if I'm asking you to get comfortable with MATLAB, I should ask you to take the test that way too. I don't necessarily like the idea of forcing you to do everything one way and then on a test, you've got a new tool in your hand, right? It's like saying I let you do everything with a battery powered drill and then I gave you a manual one or something for that. It just feels like if I'm training you one way, I should test you one way too, right? It is, yeah, yeah, and
Yeah, because most of the time we always just like look at the math like flattening out.
yeah, that's right. All right. So one last thing here is I want to do this thing is I want to get the power factor of the combination to be unity. Right? Maybe I'll talk a little bit more about why that is on Friday, but what I said was I've got the two loads in parallel with each other, S1 and S2. All right. The total power delivered to those loads, I'll call it S. That's equal to S1 plus S2. Now, if I add those two vectors, we have what those vectors are at this point. If I take those vectors and I add them together, this works out to be, you can go back and look at it later, it's 21 kilowatts plus J times 11.796 kVARs. Now, what I want is I want to make the power factor of that combination, I want it to be unity. All right, it's a fancy way of saying I want the power factor to be 1. I want the power factor of that, so I know the voltage here is V sub L across that combination. I want the power factor to be unity. What is it now? I don't know, but is it unity?
Sorry.
What's the underline?
Yeah, you go BL and you underline.
To say that it's a phasor, right? To say that it's a vector, right? That I'm talking about a vector rather than a number, right? So I'm saying here, all right, so this guy here is 21 kilowatts. Is that unity power factor? If I looked at this thing and I drew the triangle, I don't know. It's 21 kilowatts is the real part. And half of that, roughly 11.796 kVAR is the imaginary part. And then S, the magnitude of S would be somewhere like that. Is that unity power factor? No. Where would S be if it was unity power factor? It'd be all purely real. The angle would be 0. Phi Z would be 0. All right. In other words, what I would have is that S1 plus S2 would be 21 kilowatts, and there would be no 11.796 kVAR. Yeah, so what I do is I put a capacitor in parallel here. Now, what's true about a capacitor? No, a capacitor, if I had a capacitor, where would it, if I drew its power triangle for a capacitive load, what quadrant is that in? The fourth, right? So effectively, this guy would end up becoming, if I put the capacitor in there, the total power would be this minus negative J Q capacitor, right? So that means that turns this into whatever that is. So if I want unity power factor, what does the Q of the capacitor need to be? Yep. Yeah, I guess I'd be careful with this. The magnet, so Q, I'll write it as a magnitude. Let's do it that way, right? Just so we're clear, it's a positive number. Should be 11.796 kVAR. All right. So I need a capacitor that can source that much. Basically, here's what we're saying. I'm going to talk more about this later. What we're saying is right now that Q that those two loads need is being supplied by Duke Energy. So some generator somewhere is producing some current that's going out onto the grid to supply the Q. What am I doing? Is I'm saying if I need if I need a positive Q in these loads, I could supply that Q locally by a capacitor bank. All right. And if I put that capacitor bank there, it will keep the current coming down that line from Duke. It'll keep it lower. So there's not naturally a reason for you to put a capacitor in there, unless Duke gives you a penalty for saying, you know what, your power factor is so bad, you're making me shoot more current down there than you need. And that's causing me to burn more fuel, right? So what they're saying is, all right, if your power factor is too low, they're trying to incentivize you to fix it, right? So that they can reduce their costs. All right, so we'll look at that more. But basically, once I know that I need to supply that much Q, how do I figure out how big a capacitor I need to do it? I know the voltage. Yeah, so I go back to my table, and I've got in my tables here, go way back here in the notes, but in my tables, I have these. Okay, so I got these quantities here. So active power and reactive power. I see that if I know the impedance of a load, right? Reactive power basically is the V squared divided by Z, right? So you learned in circuits 1, right? So V squared divided by R is power. I'm talking about reactive power. I'm talking about V squared divided by the imaginary part of Z. So in this case, if I know, where did I do it? Got a lot of blank space here. That Q would be equal to the magnitude of V line squared divided by the imaginary part of the capacitor's impedance. What's capacitor's impedance? 1 over j omega c. The imaginary part of this, I'll say, is 1 over omega c, like that. And I end up solving with this. I need to know what the frequency is. So I told you at the beginning the frequency was 60 hertz. So if I plug in 2 pi 60, I end up with a capacitor that ends up being 723.22 microfarads. And I've got my code that I use to solve for that right there. All right, if you want to go back and look at that later. All right, and again, I'll post the notes and videos so you don't need to worry about writing it down or photographing it or whatever. All right. All right, so I think we're right at time. I'll stop there. And